Welcome to this training session on effective stress and groundwater. This is Jim Hazard, Software Development Manager at Itasca. So this section is applicable to FLAC2D and FLAC3D. I'm mostly going to be talking about version 9.1 or above. Some major new improvements have been made related to the groundwater modeling in version 9.1 and above. When it makes sense, I will also mention, how things are done in version 9, and all of the examples I've also given you the version 9 version of those examples. And I've also given a 2D and 3D version of all the examples. So I'll talk about that when we get to the examples. So effective stress and groundwater. I'll start just by talking about pore pressure and effective stress and how you can assign pore pressures. And we'll just do a super simple slope example. This is related to solving problems where you just specify the pore pressure, but you don't actually perform fluid flow analysis. Then the second part is related to actually calculating fluid flow through the system and how that works. And we'll continue on with the slope example. So pore pressure and effective stress. If you've been following along this course from the beginning, everything up until now has basically been just mechanical calculations. It is possible, of course, to consider pore pressure in these models. The real reason of considering pore pressure, of course, is that it affects the mechanics, because usually you're looking at stability or deformation or something like that. So a couple of things to note about using pore pressures in FLAC3D or FLAC2D. Formulation in FLAC2D or FLAC3D actually uses pore pressure rather than head. So if you've seen other programs like Rock Science or GeoStudio or so on, they often use head, and everything is plotted in terms of head, and all the inputs are in terms of head. The underlying formulation in FLAC2D and FLAC3D uses pore pressure. And the reason it does that is that it's independent of the unit weight of water. So in theory, you could have a different unit weight of water, and then your head would get screwed up. If you use pore pressure, then it's independent of that. And the relationship between head and pore pressure is just shown here. It's basically the pore pressure divided by the unit weight of the water. Pore pressure is stored at the grid points. Compression is positive. Sometimes you might want to query the zone pore pressure, for example, in fish, or it actually uses the zone pore pressures to work out the effective stress. And this is really just the average of the grid point pore pressures for the zone. So effective stress, the whole point of calculating pore pressures is to figure out the effective stress. So total stress is effective stress minus pore pressure. So total stress is forces on the grid points or structures and so on. Effective stress is what the constitutive models use to figure out whether or not something fails. So when it's looking at the failure envelope, it uses the effective stress to see if you are above or below that failure envelope. And then pore pressure is obviously just pore pressure, compression being positive. And again, stresses are negative, compression negative. So if you add a positive pore pressure, it makes the total stress more compressive. So imagine you have a cube and all the boundaries are fixed, and you increase the pore pressure, you're actually increasing the total stress. The effective stress becomes less compressive. By default, all the stresses you see in FLAC3D are total stresses. So if you just plot stress, you get the total stress. However, there are plot items that allow you to plot the effective stress, and this is sometimes useful. And also fish functions, as shown here. So setting the pore pressures. So if we're not actually doing a groundwater analysis, or even if we are doing a groundwater analysis, you may want to set the initial pore pressures. In version 9 and below, this is the way you can do it. Zone grid point initialized pore pressure, and you give some parameters. Or zone water, and you specify a plane or a geometric set, or zone grid point import. As I mentioned, I'm mostly going to talk about version 9.1 and above. And again, things are a lot simpler now. We've tried to simplify the way that the fluid flow analysis is done. And so now anything you want to do to initialize pore pressures starts with zone grid point pore pressure. Note that if you're following along with the PDF document, these are links to actual to the online documentation, so you can just click them and see what it says. So whatever you want to do here, you say zone grid point pore pressure initialize, and you can set some value with the gradient. You can specify a head. So like I said, the underlying formulation uses pore pressure, but to make life easier for people, you can specify a head. You can specify a plane, which is just a plane that determines the water table. Often it's horizontal, but it doesn't have to be. Commonly, especially in 3D, you might specify a geometry. So this might be a geometric set that maybe you've imported, like a DXF. Especially in 3D, this is useful. You might have a three-dimensional surface that defines a pore water table. If you import that, it will automatically use that to determine the pore pressures, and I'll show that in the example. It's also possible to import pore pressures just as points. So this would be X, Y, Z, and a pore pressure in, for example, a CSV file. It's also possible to import pore pressures from a MyDW file. If you are just setting the pore pressures and you're not actually doing a fluid flow analysis, be aware that you will need to manually specify a different density below the water table and above the water table, assuming that there's a reasonably high porosity. If you're just specifying the pore pressures, you don't have to specify porosity. So it's up to you to specify what the density is below the water table and above, and we'll show that in the example as well. So, okay, here we are in the example. This is just a simple slope with a water table. And again, I've given you a 3D version and a 2D version. The 3D version is really just a 2D version extruded one zone. It is possible to run this example with the demo version of the software. There's less than 1,000 zones here, so you can follow along everything that I'm doing in this session with the demo version. You don't actually need to have an actual license. But I'm going to do this example in 2D because it really is just a 2D example. And in 3D, it's just extruded one zone. So we start with drawing it in Sketch. So you've hopefully been following along. You've seen how to do things in Sketch. This is relatively easy. You basically draw a box, a line, a couple more lines, and you're done. And you assign the group name surface to these faces here. Well, they will become faces. And this just makes it easier later when we apply the boundary conditions. One thing not shown in this plot is we actually create the missing piece here in Sketch as well, and we can excavate that to make it a sort of more accurate solution. So let's just call up FLAC3D and have a look at what I'm talking about here. All right, I've got FLAC3D open already. Again, this is 9.1. I've given you these examples, so you should be able to just open them. So what you want to do is the file open. All right, I've got it under Documents, Training, FLAC3D 2024, Groundwater, Exercise 2D, and there it is, fluid.project. So we open the project. Okay, so the geometry.dat file is really all the Sketch commands. Okay, obviously you're not going to type all these commands. You're going to draw it in Sketch. You can run this file, have a look at the sketch. So we just draw this, we drew this slope. Look at the controls here instead of the fish. We drew this slope. And again, here's this extra piece that I didn't show in the PowerPoint. We did assign a group name to this to make it easier to excavate. So if you go up here to this little group highlighting thing, you can see one of the groups is called excavate. If I click on that, you can see this guy is now green because we grouped it as being called excavate. If you click on it, It actually appears over here, the group name excavate. If I choose group name surface, you can see this green line here shows you where I've identified these edges as being called surface, and we're going to use that later. And again, if you just click on one of them, you can see the group name surface here. Okay, so that's just the geometry. Now we're going to start typing commands, and the first thing we'll do is solve this slope dry. So if you double click on slope dry.dat, we're doing this in 3 different ways. So if you followed along with the previous examples, the first way is by excavating that excavate piece using zone relax, and this is the sort of recommended approach. The second way would be to just delete it in one shot and solve it. And the third way is to actually delete it and not even install any in situ stresses. We don't need to go through all of this. You've seen this before. This is the groundwater part, so everything I'm doing here is related to mechanical. So what we'll do is we'll just excavate with the zone relax, and then I can just put a program return here, so it doesn't execute the rest of this file. It's only going to execute test 1. Make this font a little bit bigger here. So we start by restoring the geometry that we built with Sketch. We turn off large strain. Constitutive model is more Coulomb. These are the properties. I should put here in the example KPA. So often in civil engineering, people like to use kilopascals. So this bulk modulus and shear modulus are values in kilopascals, and also the cohesion. Be careful when you're using kilopascals that the density is not kilograms per meter cubed. It's kilograms per meter cubed divided by 1,000 to make everything work out. Friction is still friction in degrees. The next part here is boundary conditions. So all it's doing is applying a normal velocity of 0 on the sides and the bottom. I think. So if I say range group top not, it means it's going to find all of the boundaries that are not called top and apply the velocity normal of 0 to those sides. We turn on gravity, we initialize the stresses. Remember that we're starting with this slope. So initializing the stresses is going to work out the stress due to gravity in this whole thing, including this piece here that we're going to excavate. We take a history, and then we solve it. It should solve really quickly. Everything should be balanced to start with. Then we excavate that piece using this zone relaxed excavate command, range group excavate, and we solve again. We delete that that piece, because remember the zone relaxed excavate command actually just reduces the modulus and so on. We can just get rid of it altogether here by deleting that group, and then we save it. So we can just run this part here. Okay, I've given you some plots here. Pore pressure, there isn't any. We haven't put any water in here yet. We can look at displacements. So you can see what's happened here. There's a little bit of sideways displacement here, and even a little bit of upward displacement, because remember we had a piece of material here that we then deleted, and so what you see is this sort of uplift due to the missing piece of material here that was pushing down due to gravity. Okay, so that's the dry solution. We solved it with the excavated piece here, which probably solved quite quickly, 200 steps. Then we excavated it and did a zone relax, took about 2,000 steps, and we get this resulting displacement. We can have a look at the state. If I change this zone displacement magnitude contour to label, and I change the label to state, we can see here a little bit of tension failure up at the top. some shear failure in the past down here at the bottom toe. That doesn't really matter. I mean, it's not shearing now. And again, you can go over here to the attributes and check this no past box and see only the things that are failing right now. There's a little bit of material up here failing in tension still. Basically, everything else is elastic, and this has come to equilibrium. So when this slope is dry, it solves. Everything is fine, no problems. All right, let's change this back to displacement. Now we can add a water table. So let's double click on slope underscore WT.dat. That's for water table. We can start by restoring the dry slope. We can initialize the displacements to 0. We don't care about the displacements so far. You know, we just want to see what happens when we add water. We can set the state back to 0. We imported DXF. So this is called water table.dxf. So we can just run the file up to here and see what we've got. If you go to the pore pressure plot, I'm actually plotting the geometry here. I've given it to you. If you haven't seen this before, you can go to plus, user defined data geometry. Click on that to plot the geometry. So here's the water table that we just imported. It's just a 2-dimensional DXF. Pore pressure to 0, we haven't used the water table yet. All we've done is imported it. So if we go back to the water table data file, here's where we set the pore pressure. Zone, grid point, pore pressure, geometry. We give the name of the geometry that we just imported, which by default is the name of the file without the .dxf extension. So pore pressure geometry water table. And in order for this thing to work out the pore pressure, it needs to know the density of water, right? You could specify that up here with a zone fluid density command, or we can just do it all in one here by specifying the density here where we initialize the pore pressure. Remember, this is kilopascals, so the density is not 1,000 kilograms per meter cube. It's 1, whatever the units are when you're using kilopascals. Okay, and remember, we haven't set a porosity here. So because we're not doing a fluid flow analysis, we don't need to set permeability. We don't need to set porosity. The program cannot then figure out what the density is of the wet material versus the density of the dry material. So what you have to do is tell it what the density is below the water table, assuming the porosity is, you know, non-negligible. It'll be heavier when it's saturated than it is above the water table. So remember the density of the material, the dry material, we set to be, I can't remember, 1.8. So the wet material, right, where did it go? The wet material is heavier than that. You can work this out. If you assume a porosity of 0.3, you can do a little calculation to figure out what this density is. So zone property density is 2.1. Range group wet. So how did we get this wet group? We grouped the zones that are above that water table geometry that we just imported. Zone group wet, range geometry space water table, count odd. This syntax is a little bit weird. What this count odd does, we may have talked about this in a previous session, but what this count odd does is, well, it's easier if I just show the plot. So here's the pore pressure plot. Here's the geometry that I imported. I say range geometry space, and what it will do is for every zone, it will project a ray upwards by default and count how many times that ray intersects the geometry. For all of these zones that are below this geometry, when I cast a ray upwards, it will intersect the geometry 1 time. For all of these zones above the geometry, I cast a ray upwards, and it intersects the geometry 0 times. So in order to identify all of these zones that are below the geometry, I say range geometry space count odd. I could have said count 1, but you can imagine a case where you might have a twisty-turny water table, and it turns out that if you're below that water table, it will always intersect an odd number of times. And if you're above, it will or if you're not below the water table, it would intersect an even number of times. So just to be safe, you can say range, geometry, space, count odd. So we can just run up to here, and I'll show you what happens. So run this part. If we go to the pore pressure plot, well, first of all, it worked out the pore pressures based on the depth below the water table. But what I actually wanted to show here was if I change this to label, and the label is group, let's change the slot to default. So what you can see here is that everything that's below the water table is called group wet, and everything that is above the water table is called group none. You can see that that worked. And now that I've assigned the group name, I can assign the pore pressure. Go back to the command. Yeah, zone grid point. Oh, because I did the pore pressure first. Zone grid point pore pressure, geometry, water table, density 1. I worked it out. Zone group wet. And then I changed the density of the material below, the density of the material that's called wet. And then we're going to solve. One thing to note here. So this command, zone grid point pore pressure, geometry, water table, it allows the pore pressures to become negative. So you can see here, the 0 pore pressure is right along this line, but above the line, we actually have negative pore pressure. Note that by default, the negative pore pressures don't have an effect on the effective stress. So the pore pressures here are negative, but the effective stress, when it's calculating the effective stress, it just assumes that they're 0. You can force it to account for negative pore pressures in the effective stress calculation, but by default, it doesn't account for them, and it's basically 0. Right, so let's just run the whole thing. Shoot, here it is. So you can see what happened here. We added some fluid. We get a little bit of downward motion mostly because the density increased. Upward motion down here at the toe. Potentially there's some extra failure occurring because we added this water. And remember, the water changes the effective stress, and it uses the effective stress to work out whether or not something fails. So we can go back and look at the state. So now you can see that some of this material failed due to the change in the water table. If we turn on the note pass, you can see that down here at the toe, this is actually still failing, which is presumably part of the reason that we're getting this upward motion. Now, one thing to note, if we run this elastically, the pore pressure doesn't really have an effect on the behavior, because again, it uses the pore pressure to calculate the effective stress. It uses the effective stress to see if something fails. By default, it doesn't account for changes in total stress due to the pore pressure. So let's just do an experiment here. Let's not change the density, because the density that is causing a little bit of this downward movement. So first of all, let's try it without changing the density. And let's see what we get. Right, so we don't see that downward movement now because we didn't increase the density below the water table. We see a little bit of sideways movement and upward movement here, mostly due to the change in the state because of the pore pressure change. If we run this elastically, so let's do this, model solve elastic only. Let's have a look at it. Almost nothing happens here. So look at this displacement is 2e minus 7. Okay. So again, by default, if we're just setting pore pressures, we're not doing a fluid flow analysis, the pore pressures affect the effective stress, which affects the failure, but it doesn't affect the total stress. So we don't see any movement here. If you want to see movement, so maybe you were expecting to see, I changed the pore pressures. I'm basically lifting up the water table from the bottom to up here. Maybe you're expecting to see some upward movement, right? You're expecting to see this sort of buoyant effect due to the raising of the water table. If you want that to happen, and you're not doing a fluid flow analysis, you need to specify that. And so what you would do is you would say, some good point, pore pressure, geometry, whatever, density, whatever, and you give the keyword effective. Now what happens is it will actually change the total stress, and you will see this uplift due to this buoyancy, even when I run it elastically only. So now if I look at the displacement, right, you can see this upward motion because we lifted up the water table, changes the total stress, it causes this upward movement. That's what you get. So sometimes this is what you want, and sometimes this is not what you want. If you're just installing an initial water table and you don't necessarily care about this upward movement, then you don't want that. And by default, you don't get it. If you're changing the water table from, say, the initial state to something else, you probably do want this effect, and so you want to use that effective keyword. Note that in the next part of this example, when we get to doing the actual fluid flow analysis, this happens automatically. There's no concept of effective versus not effective. Changing the water in the system causes these movements all the time. So, okay, so that's basically if you don't want to do a fluid flow analysis, if you just want to specify pore pressures using a water table or some other scheme, this is how you would go about doing it. So the rest of this presentation is going to talk about doing an actual fluid flow analysis. So, you know what? Let me run this again. Just so we have the correct save state when we come back to this. Okay. I'm going to minimize this and bring back the PowerPoint. Okay, groundwater flow calculations. FLAC3D and FLAC2D models the flow of groundwater through a permeable solid such as soil or rock. Modeling of flow may be done by itself. So you can model just fluid flow and not worry about the mechanical part. Or you can model fluid flow and the mechanical part. And there's different types of coupling that can occur here. It's basically a two-way coupled system. So what that means is that if you change the pore pressure, you change the effective stress, which of course can cause more yield, but can also cause movement, as I was just showing. So that's one way. The pore pressure affects the mechanical. The mechanical can also affect the pore pressure. So if you change the volume of the pore spaces, you can change the pore pressure. Imagine if you're squeezing a pore space, the pore pressure will go up. Or if you're relaxing a pore space, the pore pressure will go down. So there's a two-way coupling here. Pore pressures affect the mechanical, and the mechanical can affect the pore pressures. Just like we saw with the mechanical, you remember how we talked about with the mechanical that these simulations are always kind of dynamic, and we had a bunch of damping in there to get to a steady state. In version 9 and previous to version 9, the groundwater calculations were always transient. So it's the same sort of idea. They were always transient, and you do certain tricks to try and get to a steady state more quickly. Post version 9, so 9.1 and above, we actually added a fluid steady state command. So it will get you to a steady state very quickly. And we'll show that in the example. The code handles fully saturated flow and flow in which a phreatic surface develops. When you have a phreatic surface, you can have 0 pore pressures above the phreatic surface, or you can have negative pore pressures above the phreatic surface, like I just showed, depending on what type of saturation model you're using. By default, we have a cubic law that relates the apparent permeability to the saturation. I'll show that in a minute. Flow due to capillary pressures in the unsaturated region is not included directly. But again, depending on the model you're using, you can have negative pore pressures and you can have flow. Okay, so if you actually want to do a fluid flow analysis and you don't want to just set the pore pressures, you need to give this model configure fluid flow command. This will turn on the groundwater flow calculations, or at least the ability to do fluid flow calculations. By default, the fluid flow calculations are on when you give this command. So if you just say model solve, it will automatically do a mechanical and fluid calculation. If you turn on this model configure fluid flow, you now have to specify fluid properties for the zones. Fluid modulus, permeability, a porosity, and so on. In version 9.1 and above, all of these properties are assigned by saying zone fluid property. Everything goes to the zones. In version 9 and before, it was a little bit confusing because some of the properties went to the zones and some of the properties went to the grid points. And so we've just tried to make this simpler. In version 9.1 of all the properties are assigned to the zones. So I just put this in here in gray that to be aware that some of the properties are actually grid point properties in version 9 and before. Also in version 9 and before, the high level command here is model configure fluid rather than model configure fluid flow. I should also mention that everything that you were able to do in version 9, you can also do in version 10. Oh, sorry, version 9.1. Everything is completely backward compatible. So if you had a version 9 file, you can run it unchanged in version 9.1. Everything will work. There's no need to worry about it. But we've just tried to simplify things and make life easier for people that are new using version 9.1. And so the reason we have this model configure fluid flow rather than model configure fluid is it just sets different defaults that I think are a little bit more sensible. So if you use model configure fluid flow in version 9.1, things are a little bit easier for you. However, model configure fluid will still work and you can still use your old version 9 files. Okay, so you set the fluid properties on the zones. The grid points have a saturation. The grid points have a pore pressure, as already mentioned. Grid points also have a saturation, which may be something less than 1. When you turn on the fluid flow, you don't have to do this crazy business about trying to work out by hand what the wet density is, because you're actually specifying a porosity. And because the grid points have saturation, it will work out the change in density for you. You don't need to go and do it by hand. Okay. A little bit here about the mathematical formulation. Certainly don't want to go into detail about this. You can read about it in your own time. But just so you know the basics, FLAC3D uses Darcy flow. You can have anisotropic permeabilities. You can actually have a full permeability tensor. You have different permeabilities in different directions. Again, effective stress is used in the constitutive models. The phreatic surface will automatically work itself out depending on which unsaturated flow model you're using. Note that by default in version 9.1, it will not calculate a phreatic surface. It will just calculate fluid flow, and you will get negative pore pressures, and there will be no desaturation. If you want to see desaturation or have permeability related to negative pore pressures and this kind of thing, you can specify zone fluid unsaturated and give some model, and I'll show that in the future. In version 9 and before, you didn't have to do that. It automatically assumed that you wanted to calculate this desaturation. You can have, again, two-way coupling via generation of pore pressure by mechanical volume changes. So again, imagine you squeeze a pore space, it's going to cause the pore pressure to increase. If you relax the pore space, it will cause the pore pressure to decrease. If you want to see this effect, you need to give this zone fluid property pore pressure generation on command in version 9.1 and above. It turns out that in many cases, you don't want this to happen. You just want to calculate the pore pressures, and you want to see the effect of those pore pressures on the mechanical. You don't want the mechanical calculations to then change the pore pressures again because of volume changes. So in version 9.1 and above, this is off by default. And if you want to see this effect, you need to turn it on. In version 9 and below, this is on by default. So all the mechanical changes will cause pore pressure changes if you have a fluid modulus greater than 0. Okay. Fluid transport is just Darcy's law. Probably you've seen this before. FLAC3D under the hood uses this mobility coefficient, which is in this weird units of meters squared per Pascal second. In version 9.1 and above, you can just specify what is more common in civil engineering, which is hydraulic conductivity in meters per second, and everything will work. And you don't actually need to worry about this. Fluid mass balance, so there's an equation in there to make sure that mass of fluid is conserved. Constitutive law for a saturated material. So what this is telling you is that if you increase water content to the pore space, it will increase the pressure. Obviously, if you decrease water content, it decreases the pressure. And also, if you change the pore volume, as mentioned, it will change the pressure. And this effect depends on the fluid bulk modulus, this Kw, and the porosity. If you have partially saturated material, the behavior is a little bit different. If you add water to the system, you're not increasing the pressure, you're just increasing the saturation. And if you pull water out of the system, you're not decreasing the pressure, you're decreasing the saturation. So the pore pressure doesn't change until saturation gets back up to 1. Once the saturation hits 1, then the pore pressure starts to go up again. Okay. So when it comes to this desaturation, one of the models for calculating this is what we call the cutoff model. And so this was the only model that was available in version 9 and before. In version 9.1 and above, you can specify this as one of the models that you might want to use. Zone fluid unsaturated cutoff, and then you can give a value, which is essentially the tension that it will support. By default, it's 0. So what that means is that when the pressure hits 0, so let's say you have the pressure is decreasing and decreasing. When the pressure gets to 0, it will start desaturating. Okay, you don't have negative pressures. You just have the thing starting to desaturate. Of course, it doesn't have to be 0. You could specify another value, minus 1 kilopascal, and so that you can have some tension in the fluid. But once you hit that limit, whatever you specify, instead of decreasing more than that and becoming more negative, you will just start desaturating the system. So if you look at a plot of the saturation versus the matrix suction, saturation is 1, and then you reach that limit, whatever it is you specify, by default it's 0. You don't see any more change in pore pressure, you just see desaturation. Version 9.1 and above, you have the ability to specify other models. So you can say zone fluid unsaturated, and you can give, so the previous model I just showed you was the cutoff, which is this red line here if we're plotting apparent saturation versus suction. We also have the Gardner model, which is this gray line. We have the Brooks-Corey model, which is this blue line. The Van Gunsten model, which is this yellow line. And these are just different curves that relate the apparent saturation to the matrix suction. If you're unfamiliar with these things, you can imagine that the way that these curves behave depends on the soil type, right? So if you have something that's a clay with maybe very small grain size, you might see something like this where it can have a lot of suction in there, right? You got these very small pores. You can have a lot of suction. It desaturates slowly. Whereas if you have something that's a sand with maybe bigger pore space, you can't necessarily support that much suction, and it desaturates quite quickly. So you can represent these different types of curves by using these different models, or you can define your own by just specifying a table. We don't actually have the Fredlin-Zing model built in here, This was just done by specifying a table of points to get the sort of behavior that you want. So you can put in whatever the heck you want here by using a table or by just changing the parameters for these different material models. This plot here is straight out of the manual, so you can just go to the manual and see how this is done. So this is relating saturation to negative pore pressure. There's also a relationship between so once you have the saturation, that can change the permeability, right? So usually as the saturation goes down, the permeability also goes down. And so there's also a relationship between the permeability and the saturation. By default, we have this S-shaped relationship, which is given here. So at 0 saturation, the permeability approaches 0. And as you get close to a saturation of 1, the permeability goes back to this value that you specified. In version 9 and below, this is the only curve that you can have. This is the built-in default curve and the only curve that's available in version 9 and below. Version 9, you can again make a table of whatever crazy curve you want here to relate the permeability to the saturation. Okay. So modeling approaches. There's different ways to consider modeling the fluid flow. If you're a civil engineer, you're probably used to these terms. So drained behavior. This is basically a one-way coupling where we're assuming that the material has a high permeability and the fluid is flowing relatively quickly. And so you can imagine that you change the fluid boundary conditions. The fluid flows quite quickly. The pore pressures change quite quickly relative to maybe mechanical loading or something like that. So we can basically do a one-way coupling. We can calculate the pore pressures first, assuming that it's fast, and then do the mechanical calculation. The opposite effect is an undrained behavior. So imagine you have a clay or something with a very low permeability, or maybe a very rapid loading. The pore pressure does not have a chance to dissipate during the application of the load. So what happens in this case is we basically say that there's no fluid flow and all of the pore pressure changes are due to mechanical changes. So we drop a load on the surface and you're going to see a jump in pore pressure because we're squishing this pore space and it doesn't have time to dissipate. So that's this undrained effect. And then, of course, the gold standard here is a coupled analysis, where the load or the mechanical is affecting the pore pressures, and then the pore pressures are, of course, affecting the mechanical. And so you can go back and forth doing this fully coupled analysis. So no flow calculation. This is what we showed already in the example where you just specify as pore pressure distribution and you run it. If you turn on the flow calculation, often you will do this sort of uncoupled approach, where maybe you solve for the mechanical first, then you solve for the flow to get the pore pressures at some time, then you solve for the mechanical again to see the effect of those pore pressures on the mechanical, and so on. And you can go back and forth by calculating the flow to some amount of time, calculating the mechanical, calculating the flow to some amount of time, calculating the mechanical, and so on. This is a relatively fast way to do the calculation. The more accurate way is precisely called loosely coupled, but we basically just call it coupled. And so the way this works is you take a fluid step and you cycle to equilibrium, and you take another fluid step and you cycle to equilibrium, and you take another fluid step and you cycle to equilibrium. And this is what we generally call coupled. This is more accurate, but slower. You could be super precise about this and call something fully coupled, where you do a mechanical step and a fluid step simultaneously, and they both have the same time. They both have the same time step. That's kind of insane because almost always the fluid time step is a lot bigger than the mechanical time step. So if you wanted the fluid time step to be in sync with the mechanical time step, the fluid time steps would be very small, and it would take you many, many steps to get to some reasonable amount of fluid time. So even though this is the accurate description of fully coupled, that's not really what anybody does in practice. When we say coupled, we generally mean doing this. Take a fluid step and some number of mechanical steps, and a fluid step and some number of mechanical steps. And I'll show this in the example. So, okay, if you want to do the undrained solution, you need to use model config fluid flow to turn on the fluid flow calculations, but we're not actually doing fluid flow calculations. However, you need to turn this on so that you can specify a porosity and a fluid bulk modulus, because you need to know the porosity and the bulk modulus in order to calculate the pressure changes due to volume changes. So you say model config fluid flow, you specify a porosity, you specify a realistic fluid modulus. You turn on this two-way coupling, zone fluid property, pore pressure generation on. This is necessary in version 9.1 and above. This is unnecessary in version 9 and below. And then you just solve the mechanical part. Again, we're not doing a fluid flow calculation here. There are mechanical changes that are changing the volume of the pore space that are causing pore pressure changes. And this is what's called an undrained effect, because we're assuming that the load is being applied so quickly, or that the permeability is so low that there's not time for those pore pressure to dissipate. Show this in an example today, but there is an example in the manual. You can go and look at this. Pore pressure produced by a footing load. So here's an example where they drop a load on the surface here. And what you see is a jump in pore pressure due to that load. Again, we're not calculating fluid flow. We're just seeing pore pressure changes due to mechanical changes. Okay, that's the undrained case. The drain case, again, you also use model config fluid flow. You also want to set a porosity. In this case, you need to specify a permeability, right? Because we're actually calculating fluid flow now. Version 9.1 and above, you give this hydraulic conductivity, which is the permeability that people in civil engineering use, which is usually in meters per second if you're using SI units. Version 9 and below, there was no hydraulic conductivity. You had to use these other units that I showed earlier, which was basically the permeability in meters per second divided by the unit weight of water. Okay, so you specify a permeability, which the keyword here is hydraulic conductivity. You specify a porosity. You specify the fluid density. You specify the fluid modulus, maybe. I'll tell you why I said maybe in a minute. In this case, again, you don't have to worry about calculating the wet density and the dry density, because we're doing an actual fluid flow analysis, and there's saturation and there's porosity. It's smart enough to figure out that the wet stuff is heavier than the dry stuff. So just specify the dry density, and then we'll use the porosity and the fluid density to figure out, the actual density of the material. Now we need to specify initial and boundary conditions. Remember before, when we just threw down the water table, we didn't need to worry about boundary conditions because we're not doing fluid flow. When we are doing fluid flow, just like for mechanical calculations, you need to give initial conditions and boundary conditions. And then often you will just solve for the fluid part. So you can say model solve fluid, and it will just solve for the fluid part and not the mechanical part. All right, so here's my maybe qualification. If you are just trying to get to the steady state, so essentially you want to know what the pore pressures are at infinite time, you don't need to specify a fluid modulus. Fluid modulus is not important. You can just give this command zone fluid steady state, and it will work out what the pore pressures are at infinite time, most of the time. If you have a very complicated model with some weird saturation model, this might not actually work. It's essentially doing a big matrix inversion, and sometimes it fails. If that is the case, you can go back to doing this sort of transient analysis like you had to do in version 9 and before. But again, the fluid modulus is not really important, right? We're just trying to get to steady state. And so we can reduce the fluid modulus to some low value just to get quickly to the steady state. And there's sort of this rule of thumb here that you can use to specify a fluid modulus. Hopefully you never have to do this, because you just use zone fluid steady state and everything will work. This is the steady state case. If time is important, so now we're doing a transient analysis and we want to stop at, say, 1 day or 1 month or 1 year, and look at the pore pressure, steady state. You do transient flow. In this case, the modulus is important, right? We can't just use this hacky number here to get to the steady state quickly. We need a realistic fluid modulus so that we get the right pore pressures at the right time. However, if you're doing a fluid flow analysis by itself and you're not doing a coupled analysis, you need to account for the fact that there's storage in the solid. There's this storativity. And so you don't give the true fluid bulk modulus, you give this scaled bulk modulus that accounts for the deformation of the mechanical part. Remember, we're just doing a fluid flow analysis by itself. We're not doing the mechanical part, but we need to account for the mechanical effect to get the right behavior with time. And so there's an equation in here, but you don't have to know what it is because you just give this command, zone fluid scale modulus. And it will work out the modulus that you need to use to get the correct behavior when you're doing a transient fluid-only analysis. Then you could again just say model solve fluid time, and you give some sort of time. A more sophisticated approach is this model solve fluid decoupled, and it will alternate between doing a fluid analysis and a mechanical analysis and a fluid analysis and a mechanical analysis. And I'll show this in the example. Okay, and again, if you're doing a fluid flow analysis, you need boundary conditions. By default, the boundaries are impermeable. So if I don't do anything, it assumes that this thing is impermeable, and it will basically just fill up like a bathtub. If you have a free surface, you can fix the pore pressure to 0, right? So usually the pore pressure is 0 at the surface, unless you have standing water, but that's another story. Assuming you don't have standing water, you can specify a pore pressure of 0 at the surface. You can apply a pore pressure. So often at the sides of a model, you want to apply a pore pressure to account for the gradient in pore pressure. You can apply a discharge. This is useful if, for example, you're simulating a well, where you're either injecting into a well or extracting from a well. You can specify some discharge. Or you can apply this to the sides as well. Right, so most of the time, you're doing what I would call an uncoupled analysis. You might start out with an undrained effect to look at the change in pore pressure due to mechanical. Then you do a drained analysis, so you let the pore pressures dissipate. So step 1 is mechanical only analysis. Step 2 is a fluid only analysis. Step 3, you go back to mechanical only analysis, but you turn off the pore pressure generation, so you don't have changes in pore pressure with changes in volume. And then you can repeat steps 2 and 3, right? So let's pretend you wanted to solve to 1 day and then get the mechanical effect, and then solve to 10 days and get the mechanical effect, and then solve to 100 days and get the mechanical effect. So you can do this by hand, or you can actually use this model solve fluid decoupled command, and it will sort of do this for you automatically, flip back and forth over some number of stages. This is the way you would mostly probably do analysis in civil engineering. It's reasonably quick and reasonably accurate. If you want to be super accurate, you can do an actual coupled analysis, and you can say model solve fluid coupled, and this will automatically take 1 fluid time step and then solve for mechanical, 1 fluid time step, solve for mechanical. In this case, you give the true bulk modulus of the fluid. However, be aware that often when you have a soft soil, if you put in the true fluid bulk modulus, the fluid is so stiff compared to the soil that it's orders of magnitude stiffer than the soil, and you don't need to do that. There's no real difference between 2 orders of magnitude stiffer and 5 orders of magnitude stiffer. So we can sort of limit the stiffness of the fluid bulk modulus using this command, zone fluid modulus automatic. And what that does is it basically says, okay, I recognize that the true fluid bulk modulus is 2 gigapascals, but because your soil is so soft, I don't need to set it to 2 gigapascals. I can set it to something smaller, and my model will run faster. Okay, So that was a lot to talk about. Hopefully it all becomes clear when we do this example. So let's go back to the example. So I'm going back to my FLAC3D. And again, you have the same example in 3D if you prefer to follow along in 3D. So we looked at the dry slope. We looked at the slope of the water table. Now we're going to look at solving the groundwater. So double click on slope GW. We'll start by restoring the dry slope. Delete that excavate region. We turn on the fluid flow now. We set the displacements back to 0. We set the states back to 0. The excavate should already be deleted in the dry slope, so this probably doesn't do anything. Okay, so now we're doing a fluid flow analysis. This is different than when we just specified the water table. We need to give properties, right? So almost always you want to give a permeability, which in FLAC2D and FLAC3D you specify using mobility coefficient is the old version 9 way of doing it. Hydraulic conductivity is what most people know as permeability in meters per second. So I would say zone fluid property hydraulic conductivity, and then this is a value in meters per second. You have a porosity, and you give the fluid density. And remember, we're doing this in kilopascals, so the fluid density isn't 1,000, it's 1. By default, this will not desaturate. It will, you'll get negative pore pressures above the water table and so on. But you won't actually have things desaturating. If you want to have desaturation, you need to specify a zone fluid unsaturated model. The cutoff model is what was available in version 9 and before. So we'll just use it here, zone fluid unsaturated cutoff. By default, when the pressure hits 0, it starts to desaturate. And again, there are other models here, the Gardner and so on. And then it's a more complicated behavior of changing saturation with respect to negative pore pressure. This is sort of the simplest case where it just starts desaturating when it hits 0. You can specify some initial conditions. So I can just say initially the pore pressure head is 15. If we go back to look at our slope here, 15 is at the top. So essentially I'm saying, oh, let's just start with the pore pressure. Sorry, start with the water table at the top, ahead of 15. But really the pore pressure is 0 at the surface, right? So we're assuming there's no standing water. We're assuming the pore pressure is 0 at the surface. And remember when we built the sketch, we identified those two lines called surface, right? So this green line and this green line will have a pore pressure of 0. In theory, you could specify a pore pressure of 0 at the top too, but it doesn't really get there, so it doesn't matter. The boundary conditions on the two sides. So on the left side, the water table's at 5 meters. And on the right side, the water table's at 14 meters. So again, if we go look at our picture. So the water table will come up to here on the left side, and will come up to around here somewhere on the right-hand side. So again, you can see the water table is not going all the way up to the surface, which is 15. We're assuming that it's actually only goes up to 14. And we should see a little bit of this at the top desaturate. And we should see some sort of water table form with a curve like this. Take the history of a pore pressure at some point. We'll take a history of the total fluid time. And if all we want to do is get to steady state, we can just give this zone fluid steady state command. And in theory, it should solve super quickly. Again, it just does a big matrix inversion and gives you the steady state, and it basically does it in one step. Note that I haven't specified the fluid modulus here, because if all I'm doing is getting to the steady state, I don't need to give the fluid modulus. So I can just run this up to there. Right, so you can see that was basically instant when it did this solving there. I can go and look at my pore pressure plot. Right, so I can see what happened here. So remember that The water table is at 14 meters on the right side, 5 meters on the left side, 0 on the surface. I said solve to steady state, and when boom, it solved to steady state. This bottom plot here is showing saturation, so you can see how it desaturated above this, where the water table forms. I can actually plot the water table in 2D. I go to the plus, under miscellaneous, nope. All right, under zone, there's water table. So it plots a green line here. And the way it plots the water table is it just looks at the boundary between saturation of 0 and saturation of 1 and puts the water table in between. We can change the color here. Let's make it black. So you can see that steady state command did a good job here. It's giving me a realistic looking water table. It's giving me some desaturation. So far, this is just the fluid flow part, right? We haven't done the mechanical part, so displacements are 0. Well, let's change this back to displacement. We haven't done that part yet. I'll go back to my file. Now I want to do the mechanical part. Zone fluid property density saturated off. So if I want to have different density, if I want the unsaturated part to have a different density than the saturated part, I need to give this command. Zone fluid property density saturated off. So it means it will use the dry density if the saturation is 0. And then I just solve for the mechanical part only. So I say up here I said zone fluid steady state. To solve for the mechanical part, I say model solve static. It assumes that I mean just the mechanical. Solve static means mechanical only. I can use this convergence 1 as the solve criteria, and then I can save it. So let's do this. Solves quite quickly. Now I can go look at my displacements. I can see, again, some downward displacement, mostly due to the change in the weight of the material, right? So essentially what we did is we lifted up the water table from the bottom to 14 meters over here, and that causes this material to become heavier because the porosity is 0.3, and so we get this sort of downward movement in the end, a little bit of upward movement here at the toe. Okay, so that's how you do a steady state solution. Super easy. Zone fluid steady state, followed by model solve static. Transient analysis looks a little bit different. Let's start with the the model that we just solved, and let's pretend we're going to drop the water table by 1 meter. So let's reset the displacements. We'll drop the water table by specifying a head of 13 on the right-hand side. Now we're doing a transient analysis, so the fluid bulk modulus is important. Okay. The true fluid bulk modulus is around 2 gigapascals. Oh, that should actually be 2E6, because remember we're doing kilopascals. So 2 gigapascals is actually 2E6 kilopascals. Now, because we're doing only a fluid flow part here, we're not doing the coupled part. We're not doing true coupling. We're going to do just the fluid flow part. We need to account for the mechanics. We need to account for the storativity, the stiffness of the solid material. And so there was that equation, and you could go and work it out by hand, but you don't need to do that anymore in version 9.1. You just give this command zone fluid modulus scale, and it will work out what the fluid modulus should be to account for the fact that we're only doing fluid analysis. Now, here I could just say, I could do something like this: model, solve, fluid, time, and give some time, and it will just solve the fluid up to that amount of time. And then I could say model, solve static, do the mechanical part, and I could repeat this over and over again, right? Model, solve, fluid, time, some other time, model, solve static again, right? So I could do 1 day, 2 days, 3 days, 4 days, and so on. In version 9.1, we've tried to make this a little bit easier by giving you this command, model solve fluid decoupled. You give it time, you give a number of stages. And what this will automatically do is take this time divided by 5 for 5 stages. It will run 1/5 of that amount of time fluid, then do a solve mechanical, then run another 1/5 of that time fluid, and then do a solve mechanical, do another 1/5 of that time fluid, and then solve mechanical, and so on. And you can actually set it up to save at each one of these stages if you really want to. We won't do that here, but you can. So this is just an easy way to do this sort of decoupled analysis, whereas you do fluid, solid, fluid, solid, fluid, solid. So we can just run this whole thing. See, you can see that it's doing flipping back and forth between fluid and solid here. In the end, the total fluid time is 5.18 E5. And we've solved to some converged state. You can look at the pore pressures, more or less the same as we saw before. You can look at the displacements, similar to what we saw before. That we did this a little bit more accurately by doing solid and fluid rather than just fluid. Oh, sorry, this is just due to the drop in the water table, right? So sorry, if you look at the pore pressure, the water table should, in theory, be lower. And the displacements are a result of just lowering that water table a little bit. So this kind of makes sense. We see a downward movement due to the lowering of the water table. Okay, so the last thing here, this is the way you would probably do it in most of the time in practice. Oh, one other thing I should mention here is in version 9.1 and above, we've added implicit solver. This ran very quickly because it's a very small model and it's 2-dimensional. If you had a bigger model, it could potentially run slower, especially if you have a large contrast in permeabilities. So imagine you had like a very low permeability zone inside of a high permeability model. It will calculate a fluid time step that's quite small. If you use this implicit approach, the whole thing will go faster. So you can say zone fluid implicit, this servo on. What that means is it automatically works out the time step, and it tries to use the most sensible time step in the implicit solution. So I could run this. It actually goes faster. It's not really noticeable in this case because the model is so fast anyway, but in a bigger model or a model with permeability contrast, it definitely makes a difference. Okay, last example here. Again, this is how you would do it in engineering practice most of the time. If you wanted to be super accurate about this, we'll do exactly the same thing. We'll drop the water table. In this case, we're doing the true coupling. You use the true fluid bulk modulus because we're essentially doing mechanical and fluid at the same time. So we don't need to scale that fluid modulus to account for the fact that we're not doing mechanical. So we could just do this. However, to make it run faster, we can scale the fluid modulus down a little bit because, again, as mentioned, this modulus is, that should be 2e6. This modulus is way stiffer than the soil. And so this will intelligently just scale it down a little bit so that it runs faster. In this case, we're doing true coupling, so we want pore pressure generation on, meaning that whenever we do the mechanical, it's changing the pore pressure. And whenever we do the pore pressure, it changes the mechanical. Reset the displacements, take a history of displacement at some point. Again, we can turn the implicit on if you want to. Probably doesn't make a big difference in this example, but it could in a real example. And now you say model solve fluid coupled, and you give some time. And it will automatically flip back and forth between mechanical and fluid. The difference here is that it does it much more tightly coupled, right? It takes one fluid step and solves for mechanical, takes one fluid step, solves for mechanical, takes one fluid step, solves for mechanical, which is different than what we did before, where we solved fluid to some amount of time. So it's multiple fluid steps and then solve mechanical, and then multiple fluid steps and solve mechanical. This is just tighter coupling, more accurate. And also with this pore pressure generation on, the mechanical affects the fluid, as well as the fluid affecting the mechanical. We can loosen up the convergence criterion here a little bit. By default, the convergence will be 1. You know, again, because it's solving to mechanical convergence with every fluid step, it does take some time. So we can speed it up a little bit by loosening that convergence criterion. So we can run this thing. So you can see down here, it's taking a bunch of mechanical steps for every fluid step. And you've got a number of cycles is like a total number of cycles. And then you have the super total, which is basically the number of fluid cycles. So in the end, we get to the fluid time that we wanted. It just took quite a bit longer than it did with the previous method. So we should see pretty similar pore pressures here. You should see, interestingly, we see different displacements. Again, this is potentially more accurate than the transient response. So with the mechanical affecting the pore pressure, this might be causing some of this movement here at the toe. But the displacements are pretty small, so that's not really a big deal. Okay, that's the end of this example. And that's the end of this session. Thank you for joining. And that'll be all.